strings in the future. Thank you. Put that there, and I'll just hold this. Okay, details for me. Sorry about the size. Default Google Slides font, so I didn't mess with it too much. Charles Nutter. I'm Headius, H-E-A-D-I-U-S, on most services online. Based in Minneapolis, Minnesota, so this is a lovely warm day for me today. I've been at Red Hat for about 4 years now, working full-time on JRuby, and working full-time on JRuby since 2006. So just quick thank you to Sun Microsystems, rest in peace, Engine Yard, and Red Hat for keeping the JRuby dream alive all these years. Okay, so here's the agenda. I don't have a lot of time, so we'll just jump right in. So, talking about strings in Java. I've been doing Java since the beginning, since 1.0. It's always been a character array and a length to go along with it. Other bits and bobs in there sometimes to, like, say, cache hash codes and such. And in the beginning, UCS2 was fine. That was a totally satisfactory representation. Because 16 bits per character should be enough for all the characters in the world, right? Well, it turns out that's not quite true. So later on, it was moved to UTF-16. We keep the 16-bit characters. We have to sacrifice constant random access time for certain types of characters in the higher planes, like emojis, for example. But generally, we still have constant access time, and it still fits in the typical character size. Now, one of the biggest problems that comes up for a language like JRuby that has a very different sort of string is that string itself is just pervasive throughout Java APIs. We got char sequence too late. It was an underpowered interface, and just nobody really uses it. So we have to be able to fit into string APIs, or if we're going to use our own string, we've got to actually roll an entirely new version of it that doesn't require Java strings. So that's kind of a difficult problem for us. Recently, there's been work to improve the packing of ASCII bytes. So 7-bit ASCII in OpenJDK 9 and Java 9 will actually be able to represent itself as a compact array of bytes under the covers. So you don't have that waste of 8 or 9 bits for every single character. And there's a possibility I've heard that maybe we could even get UTF-8 in there. It'd be kind of an opt-in because of the expectations of constant random access time, but I would turn it on because I would love to just be able to pull UTF-8 bytes off the wire and not deal with anything, not do any transcoding. And this is pretty much it. This is strings on Java. They're going to be UTF-16, and if that doesn't work for you, then you're just kind of stuck. Okay, so problems here. The constant encoding overhead. Anything that you do when you have to read from the wire, read from the file system, and deal with characters, you've got at least the decoding cost of bringing it in from bytes into characters, because it needs to turn into UTF-16, vanishingly small amounts of I/O on the actual internet or on the real networks, and actual files are in UTF-16. So you pretty much always have to suffer through this. And that's not cheap. That's a cost. And then if you're going back out to the wire, most of the time if you process these characters, you're going to do something with them that sends them back out. You've got the encoding cost all over again. So it really does limit how we can do high-speed I/O, anything that you need to process characters for. Like I mentioned, the ASCII waste. So if you're just using the bottom 7 bits for ASCII characters, then you're wasting at least a full byte for every character. And early on, that was one of the things that Java haters really got into. Like, every string is now twice as large, even though I don't need it to be twice as large. It's kind of funny that we have a whole stack of like super compact byte codes to try and fit more byte code into our set-top box in 1995, and yet UTF-16 strings that waste way more than those byte codes ever would. So interesting decisions there. So we also have to deal with the fact that in Ruby, binary data is also represented in the same structure. The string is basically just a wrapper around bytes, and it might be binary, it might be characters. Really hard to do with Java. It wants those characters to be valid. If you start shoving bogus characters in there, all sorts of weird things will break. You might wonder why we would want to do this. Well, we've got various cases where we want to embed arbitrary binary data into a class file or into a constant pool. There's no good way to do this other than forcing it into a string, probably invalid string, and then shoving it into the class file itself. So that's another issue that we've had to deal with. And then there's the CJK problem, the Chinese, Japanese, Korean problem. Basically, the issue here is that each of these languages have their own representations of certain characters, like kanji and Hanzi in Chinese. The Unicode folks decided that the character that looks like this in Japanese is the same as the one that looks pretty much like this in Chinese, and so they get 1 code point. Well, you can imagine they weren't very happy about this, because now round-tripping through UTFs, through any Unicode encoding, you will lose which of those 2 versions it actually was. You can't take it back out and have the original character. In their estimation, that's a stonable offense, and it's a real serious problem for them. So that's why in Japan they still use Shift-JIS, in China they use Big 5 and other Chinese encodings because of this problem. So, strings in Ruby. Strings in Ruby are basically just a byte array and length, similar to the character array and a length in Java. And the length in this case refers to the byte length, not the character count. Up through Ruby 1.8.7, there was a single global encoding that you could set. At the command line, I think it would default to assuming it's ASCII, but you can do some Unicode operations. You could specify that all strings were Unicode, and then it would do some additional character validation, or specify some other encodings like Shift-JIS. And like I say, some operations that were specific to Unicode were always available. Like regular expressions have a flag that says treat this as a Unicode regular expression rather than an ASCII one. And that worked okay, but in a world of many encodings and dealing with the wider internet and lots of files and different formats, they decided they needed something better to negotiate all these different encodings and strings. And so in Ruby 1.9.1 and from then on, in addition to having the byte array and the length of those bytes, they had an arbitrary encoding. And that might be UTF-8, might be UTF-16, it might be Big 5, it might be EBCDIC. There's a lot of different encodings. So they opted to basically say, let's let each string decide its own encoding, so that when we do have to deal with disparate sources of data, we don't have to transcode everything to some intermediate. We can actually use mixed encoding strings throughout the system. This is obviously very complicated. We had to also implement this to keep up with Ruby features, and it's taken years for us to match up with the level of compatibility we needed for C Ruby, but it does work surprisingly well. Most of the time, you don't have a lot of mixed encoding environments. Usually, it's like a UTF-8 that you're dealing with. But if you do have mixed encoding environments, it negotiates this stuff pretty well. So it's a complex design. Some would say over-complex, but it works surprisingly well. So problems with Ruby's multilingualization is what they call it. So by default, it's UTF-8. And so the standard UTF-8 problem of not having constant random access time. You can't just say, give me the nth character and have it immediately. It has to be a walk of all characters because they're variable widths. If that's a problem for you, however, it has support for UTF-32. And so you could say, internally, I want to use all UTF-32, so it's all constant access time, and you can get around this. And it works just fine that way, too. And then, of course, you have to pay the encoding and decoding costs. Like I say, it's possible to have an arbitrary number of encodings floating around in the system, but it's rarely done, and it's almost never a problem. Usually you're dealing with one encoding, or you're trying to convert, you do actually convert things into UTF-8 and use that internally. So that doesn't come up too often. If you've got lots of strings with different encodings, every time you do a string operation with another string, you've got to find some common ground there. And there's various heuristics that Ruby uses to say if it's a UTF-8 over here and it's Shift-JIS over there, we'll negotiate it to whatever the best common encoding for those two is. And your resulting string will be one of those encodings. Most of the time, you never even need to look at this. The Ruby subsystem hides the fact that it's a byte array and an encoding, and you just deal with code points and characters most of the time. The bigger one is that all of the support libraries have to be able to do this. And as far as I know, there's only one regular expression engine in the world that can basically work over arbitrarily encoded bytes. And that's the one that Ruby imported called Oniguruma that we ported for JRuby. And then, of course, I/O needs to have a much more complicated pipeline for reading in bytes, turning them into some internal coding, and then going back out, because we handle arbitrary number of encodings. Like I said, it's complex, and the early implementations were fragile, but it has matured pretty well, and things generally just work. How are we doing here? Okay. So strings in JRuby. Prior to 2006, we did have a Java string-based or character-based implementation. But obviously, all these different encodings were a problem. Representing binary data was a problem. We realized we had to follow the Ruby approach a little bit more closely. Unfortunately, that meant a lot more work, and up until maybe even last year, we were still working out the bugs in our implementation of multilingualization. Character logic that had to be duplicated, the regular expression, we had to port that regular expression engine over, all of the I/O encoding and transcoding logic had to be ported over. So it's been years of work. But it works now. We have very few or no known bugs compared to CRuby in our encoding library and our regular expression library, and they're just Java libraries that you can use. So that's what we're going to show today a little bit. So here's the libraries that we have. I won't talk in depth about byte lists. You can just imagine it's a string buffer for byte arrays. Pretty much all there is to it. Aggregates the same things that a string does, an array of bytes, a byte length, and an encoding, and then provide some operations over those to add and insert and whatnot. JCodings is the encoding subsystem. And so this has all of the metadata for all of the different encodings that are supported. Like, if I see this byte, how many additional bytes do I need for a multi-byte character? Or given this code point, what are the bytes that this encoding would represent those as? So functional things like going back and forth between bytes and characters or code points. It also has a rather complicated inner loop of a transcoder that can take a byte array on one side that is known to be an encoding A and output it to a byte array on the other side in another encoding without doing any sort of intermediate step. In order to do this in Java, you would need to decode everything to UTF-16, re-encode it back into the other encoding, and wasting all that time in between. And so in general, the encoding logic that we have, the transcoder here, can do those sorts of conversions significantly faster than Java can. The regular expression engine is a port of the engine that the CRuby folks adopted called Oniguruma. Oniguruma is basically a regular expression engine that it can work on arbitrary encodings, and it has pluggable syntax. So there's multiple different versions of regular expression syntax, as well as being able to use any encoding. It's the most customizable regular expression engine that's out there, for sure. And our port of it actually has better performance than Java util regex for doing matches. Plus, you don't have the cost of having to pull in bytes as characters before you start doing your matching. You do a read, do your matching, send it back out, no characters involved, no transcoding involved. It's pretty cool. Okay, so a little bit more detail about JCodings. Like I said, it's all the character data and the metadata for the different encodings. Lots are supported, all the ones that you would typically use and several that you will never want to use. Actually supports more encodings than the default set of encoding, decoding logic that's in OpenJDK. And at least one of, I think ISO 8859.11, I have a patch that I don't know if I've gotten in yet to add decoders and encoders for Java. But yeah, very complete encoding support. All the weird Asian and other European encodings that you don't see often except in those countries. And then all the IBM and Windows code pages are even in there. So it supports all this stuff. You can do this direct transcoding like I talked about. Basically take bytes to bytes without any intermediate step, much faster than going through UTF-16. And that was an epic piece of code. If you ever want to see some interesting code, the C code there had nested switches and nested loops, and then branches and go-tos that would go out to other switches and cases. And that was a fun week porting that to Java. So bonus features that are kind of cool. You can have it replace anything that is not a valid XML character with its entity representation just along the way as it's doing encoding or decoding. You can also have it negotiate carriage return line feeds, normalize them all to carriage return, write like CRLF on the way out and carriage return on the way in, various levels that you can configure that. And lots of folks are actually using this in the wild. Obviously, JRuby uses it. The Facebook guys use it for some high-speed character I/O where they need to process stuff and send it out quickly. They didn't want to pay the decoding and encoding cost every single time. Truffle Ruby obviously uses it because they grew out of JRuby. And JetBrains, for any Ruby-related stuff, they use it as well internally. So here's a quick, simple example of just some of the metadata APIs. So we've got our UTF-8 bytes here, 7 bytes long for a 5-character string. We can see what the actual character count of it is by going to the UTF-8 encoding and asking it to count it up. We can see how wide an individual character is at a particular offset, so we know how many more bytes to read. And then we can go back and forth between code points, bytes to code points and back again. So simple stuff, but all the things you would need to go back and forth with bytes and characters. Here's the transcoder. So we open a new transcoder from UTF-8 to UTF-16. We've got our source and destination bytes here. And this is actually a test that's in the J-coding suite. And then we do our convert. So we've got our source. We need to pass, essentially pass by pointer the start position for this, and it's going to let us know how far it was able to decode. Where we want to start, the destination array, the destination start, and again, it's going to be different amounts of bytes depending on which encoding we're going to, so we need to get that out again. Love to have multiple return values here. And then the other details about the destination. The 0 there is flags for other things, like changing slightly, how it handles invalid characters, whether it reports it or raises exceptions and so on. So similar to Java util regex there. And then we actually can do our conversion and get the bytes out, never have to pass it through characters in the middle. So Oniguruma, Joni, is our port of it in Java. This has been pretty well functional for years. We have occasional updates and fixes, but it's been working for quite a long time now, so it's fairly stable. It is a bytecode machine, and it's stackless, which is very important when we talk about some failings of Java util regex. There's certain structures of regular expression that the existing implementation will deepen the stack for, and then deepen the stack, and then deepen the stack. So there are cases that you cannot match with Java util regex over like very large input because it'll blow the stack out. Obviously, this doesn't have that problem because it's stackless. Like I say, highly configurable, different grammars. There's a syntax for Java, for Ruby, for JavaScript, for a couple different other languages. You can pick which syntax you're using for your regular expressions and just plug it in. And again, lots of users in the wild, including JRuby. Nashorn did a version, a modified fork of this that is all character arrays. So it doesn't have the advantage of different encoding support, but it's much faster, matches JavaScript's syntax, and so on. Okay. So here, just a couple quick Joni examples. We have our regular expression we can create with just a simple string pattern or specify a different syntax that we want to use with it. Here we got our matcher, just like in Java util regex. We do our search, and the options here provide various ways of doing those matching and altering how it does the search. And then one of the other nice features here that's not in Java util regex, if you have a regular expression that's a weird case and runs forever, you can do just a normal thread interrupt and kill that match. So you don't get stuck in some inner loop of a regular expression that's never going to return. Last part of the Joni examples here. So here we want to get our regions out for pulling groups off of this. And we can get a start index and an end index, and basically just go directly to the bytes. We don't have to turn anything into characters. We can go back to the same byte array, do no copying, and have regular expression matches with groups. Okay. So just a quick note on performance. Like I said, J-coding definitely is faster than going through UTF-16. Hard to compare it other than that because it doesn't match the same way that char sets work. But it's pretty good performance. Joni can be significantly faster than Java util regex. I mean, there's certain cases where Java util regex just blows up, but 2 to 3 faster for most of the things that I've tested. So if you want to pull bytes off the wire really fast and do quick matches against them, this is a great one to look at. And being interruptible is great. Like I've had plenty of regular expressions that just went off into the weeds and never seemed to come back. It's nice to be able to kill those off and re-examine it. Okay, so wrapping up. So Java string, really unchanged for decades as far as the internal implementation, is starting to evolve some of these features. The support for compact ASCII strings and so on. Hopefully that process will continue and we'll get a more robust string that cuts some of that overhead out for us. And learning from what Ruby's done and what we've ported and re-implemented in JRuby may advise some of those features in the future. So hopefully we'll be able to help improve Java string in the future. But meanwhile, these libraries are available. If you take a look under the JRuby organization in GitHub, they're all right there, bytelist, Joni, and JCodings, and they're all in Maven. So you can pull them down and they're ready to go. And that's all I got. Thank you. Do we have a little time for questions? Yeah.
Hi. So the Java string methods like string index of or string compare or things like that, they are heavily optimized with intrinsics, and they can use vector instruction and stuff like that. So how do you compete with these operations on your class?
Well, that's a good question. I'm not sure where we stand on that. We have done some of the unsafe tricks that folks have used to do, like 64-bit stride for string searches and so on. And those help get us pretty close to where the Java performance is usually. Mm-hmm. We haven't done a whole lot of exploration because, again, it's a weird comparison. We're working with bytes and generally non-constant access time, UTF-8 handling along the way, versus UTF-16 strings, which are just read right out. So, but I would imagine we probably are reasonably competitive. I'd like to run some more numbers, though.
Okay, thank you.
All right. Well, see you around. Thanks.